Hey everyone, this is Parkav Suthar, and today we are going to learn a very important relation, that is an equivalence relation. So in this session we will discuss what is an equivalence relation and we will calculate some of the examples. So what is an equivalence relation? So let capital R be a relation in a set A. Then capital R is said to be an equivalence relation on A, the set A, if and only if the first one, R is a reflexive relation. We all know that what is a reflexive relation. So that is for every A belongs to A if A is related to A. So that is a reflexive relation. Now the second condition is R has to be a symmetrical relation. Now what is a symmetrical relation? So if A is related to B, then B has to be related to A with the same relation. So that means if A is related to B, that implies B is related to A. So it has to be a symmetrical relation. And third, R has to be a transitive relation. And what is a transitive relation? That is, if A is related to B, B is related to C, then A has to be related to C with the same relation. So it is said to be an equivalence relation if it is a symmetric, reflexive, transitive. So reflexive, symmetric and transitive. So the diagram of an equivalence relation will be, see, we have 3 points. So let us take 3 points, A, then B, and then C. Now as it is reflexive, it has to be related to itself. So all points has to be related to itself. So we will draw the loops like this. So A is related to A, then B is related to B, and then C is related to C. Okay, now just draw this. So it is a symmetrical relation. So if A is related to B, B is related to C, then C is related to A. Sorry, A is related to C. Now just draw CB, this and this. So how, see, if A is related to B, so here you can see that A is related to B, B is related to C, and then C is related, then A is related to C. So you can check for any pairs of 2. Okay, so you will get the idea. Now let us take example. Now let I be the set of all integers. Now let R be defined over the set I by A is related to B. The relation is given if and only if A minus B is an even integer, where this AB belongs to I, that is the set of all integers. Then show that it is an equivalence relation. Now all we need to do, just check all those 3 relations. That means it has to be reflexive, symmetric and transitive. Then we are through. So then it is an equivalence relation. So the first one, since for reflexivity A minus A equals to 0, that is 0 is an even integer. So that means A is related to A for each and every A belongs to A. So hence R is a reflexive relation. Now for symmetric. So now if A is related to B, now for symmetricity, if A is related to B, then B has to be related to A. So let us take if A is related to B, then what? Then we can say that by the definition that A minus B is an even integer. Yes. Now can we say that if A minus B is an even integer, then B minus A is also an even integer, whatever, plus or minus, but it will be an even integer. So B minus A is an even integer. So that means we can say that B is related to A. So that's it. It is proved. So if A is related to B and B is related to A, then it is a symmetrical relation. Now for third one. Now for transitivity, if A is related to B, B is related to C, then only A has to be related to C. So first we have to assume that A is related to B and B is related to C. Now by the definition of relation, A is related to B. So that means A minus B is an even integer and also B minus C is an even integer. Now see, A minus B and B minus C, they both are an even integer. So can we add them? So yes, we can add them. So A minus B plus B minus C is an even integer. Now minus B and plus B, that is 0. So what is left? A minus C. So that is also an even integer. So A minus C is an even integer. So by the definition of a relation, what we can say, A is related to C. So that's it, it's proved. If A is related to B, B is related to C, then A is related to C. So hence R is a transitive relation, and since it is reflexive, symmetric and transitive, the given relation is an equivalence relation. Easy. Now let us discuss second example. So let capital X equals to 1 to 7. So set is given 1 to 7 and R is set of all xy such that x minus y is divisible by 3. Then show that it is an equivalence relation and also draw graph of R. Okay, so the set is given from 1 to 7 and R is given, that is x minus y is divisible by 3. So let us understand how to do it. So here x is 1 to 7 and R is given. Now see, R is x minus y is divisible by 3. So we can write like this, set of all xy such that this x minus y equals to 3k, where k belongs to z. See, x minus y is divisible by 3. So what does that mean? It is a multiple of 3. So that means x minus y equals to 3 times some k, where k belongs to set of all integers. So x minus y is divisible by 3. That implies x minus y, it is multiple of 3. So we can write x minus y equals to 3 times some k. Okay, so now we will consider this R. Both are same. Now for reflexivity, here x is related to x for every x belongs to x. Why? Because x minus x equals to 0 and 0 is divisible by everything. So 0 is always divisible by non-zero finite number. So it is divisible by 3. So hence x minus x equals to 3 times k, k belongs to z. So it is related to itself. So hence we can say that R is a reflexive relation. Clear? Now for symmetricity. Now if x is related to y, so by the definition we can say that x minus y is divisible by 3. Now x minus y is divisible by 3. What does that mean? It means that it is a multiple of 3, and for multiple of 3 it means that x minus y can be represented like this, 3 times k. So x minus y equals to 3k. Now see, if we take minus common, so we'll get y minus x equals to 3 times minus k. So minus k also will be in z, so that means y is related to x. So that's it. Hence R is a symmetric relation. Now for transitive relation, let us assume if x is related to y, y is related to z, then we need to prove x is related to z. Now x minus y is divisible by 3 and also y is related to z, that means y minus z is divisible by 3. Now x minus y is divisible by 3, that means they are multiple of 3, both are multiple of 3. So that means x minus y can be written as 3 times some k1, and in same manner y minus z equals to 3 times some k2, and both k1 and k2 belongs to z. So this can be written. Now if we add both this, so what we'll get, x minus y plus y minus z. So y and minus y, that is 0. So what is left? So x minus z equals to 3 times. In right hand side we are adding this, so k1 plus k2. Now just take k1 plus k2 as some another k. Okay, so x minus z equals to 3 times k, where k is k1 plus k2, and that will also belongs to z. So hence we can say that x minus z is a multiple of 3. And what does that mean? X minus z is divisible by 3, and hence x is related to z. So hence it is a transitive relation. Now see, it is reflexive, symmetric and transitive, so it is an equivalence relation. So hence here the R is this and x equals to this. Now we want to draw the diagram of this. Now in the relation we won't write the relation, we will directly draw the diagram. How? Because it will contain so many points. So first, how many points are there? There are how many? Total 7 points are there. So first we will write, first we'll draw all these 7 points. That is, take 1, then take 2, then take 3, then take 4, then 5, then 6 and 7. Now we have the relation as x minus y is divisible by 3, but we can say that each and every point is divisible by 3. That means see, 1 minus 1, that is 0, is divisible by 3. So that means 1 is related to itself, 4 is related to itself, 3 is related to itself. So each and every point are related to themselves. So we will draw the loops. So 1 is related to 1, same way 2 is related to 2, then 3 is related to 3, then 4 is related to 4, then 5 is related to 5, 6 is related to 6, and 7 is related to 7. Now Now the subtraction is divisible by 3. Okay, so just fix 1. So 1 minus 4. Okay, 1 minus 4 is divisible by 3, so that means 1 is related to 4. But 4 minus 1, that is also divisible by 3. So this, oh, 1 4 1 and 1 4 will be there. Then next 4 7 and 7 4, because their subtraction is also divisible by 3. And last 1 7 and 7 1, because 1 minus 7 and 7 minus 1, that is 6 and minus 6, that is also divisible by 3. Now for 3 and 6, their subtraction is divisible by 3. So 3 6 and 6 3 pair will be there. So 3 6 and 6 3. So this is will be there. Now for 2 5 pair, their subtraction is divisible by 3. So it will be like this, 2 5 and 5 2. So this is how you can draw digraph of the equivalent relation directly. Now just try it yourself. I'm giving you one example. Now show that this congruent modulo n is an equivalence relation, and its notation is A congruent B mod n. So in short, congruent modulo B. Now the hint is, see, if A is congruent modulo B, if and only if n divides A minus B. So that means A minus B is a multiple of n. This will help. Thank you.